So if you can see my screen, I'll start. Hello, everyone. My name is Fahd Khan. I'm right now in Pakistan. I am the principal investigator and director of HBL Center for Blockchain and Applied Research in university here. HBL is basically Habib Bank, which is the largest bank of the country and one of the largest in Asia as well. And while preparing these slides, I was wondering if I would get very academic. I'll try to not be and try to show results. So basically, I was one problem that we see very common is about the applications of AI in cybersecurity, which is a very critical aspect of for every financial institution. And the distributed nature can basically blockchain can be incorporated into it to make it more credible. And so that's why I started working on distributed AI with a bunch of collaborators. And I'll start with what we have done and the results, which are quite encouraging. Now, in principle, I would start with the basics. There are two basic concepts. One is about federated learning, which is basically used to train machine learning algorithms by using multiple data sets, which means that every node connected to a centralized server gets to keep its data, and they don't exchange that data. That means that any institution who do not want to share it don't need to, but they can basically train their models locally in their within their institution, and then just share the weights of that machine learning model. And an aggregator, centralized aggregator, basically makes the averages of all those weights and then sends it back to every node to further improve. So, and distributed AI, on the other hand, actually focuses on distributing the architecture for training machine learning models, but data basically is usually centralized. So the advantages of federated learning is basically you get to train machine learning models without actually sharing the data, which is great privacy, because that's of great importance for many of the institutions who do not want to share their data with others, as opposed to distributed AI, which is using centralized data, and the communication between the nodes or the servers that are basically training those models is quite frequent, which increases the bandwidth. Now, we first used distributed CNN, which is convolution neural network. This is just the traditional. Typically, the traditional CNNs are distributed onto different nodes, and there is a centralized server from where they collect the data, train their models. But the training model itself is basically distributed into smaller, into different nodes. The computation itself, which improves reduces the training and inference time, which is a good plus, and it can handle large data sets. We run multiple nodes of this training script, and the average gradient amongst the different nodes is then shared amongst others. Now, this is there were a few problems with the distributed artificial intelligence algorithms, in the sense that there's no data privacy. There has to be a centralized server where you have to access. And this is much of a problem for the large institutions. There are scalability issues, there are infrastructure complexity, because the nodes are communicating quite frequently. The cost goes up. So we compared that with federated learning, which allows multiple institutions to collaborate without actually sharing their data, which ensures their privacy. And centralization in general is slow. So these individual corporations or institutions can use their own underutilized resources or servers and just share the weights of their learning with other institutions. Now, there are learning. Usually the clients, let's imagine there are 3 hospitals, and each hospital has the same different customers, different patients, but the same kind of age or same kind of problems or ailments. In vertical federated learning, actually, it's different institutions, more like a bank and a retail store, where the same person could go to a bank, but for be asking for a loan, as opposed to when the same person goes to a something. So you can have different kinds of data about the same people in vertical federated learning. In horizontal learning, you can have the same kind of features. So it depends on the application. We use it for in malware detection in distributed environments. So malware is basically any software that can damage or gain access to a computer system. And this work of our used the traditional malware detection faces a lot of challenges in its efficiency and scalability. Now, I won't go into the how what we did, but we used different data sets to basically make grayscale images of different types of malwares that can exist, and then capture its attributes and some kinds of features that can be used to identify malware. Now, in distributed CNN, the weights are updated through a back propagation. I don't want to go into a lot of technical details, but these gradients are updated on a centralized sort of CNN model. The thing I think the audience would love to know is what were the results of distributing these convolution neural networks. And as you can see in the slide, the centralized CNN model had an accuracy of 85% and a training time of almost more than an hour. But as you can see, as we increase the number of nodes from 2 nodes to 4 nodes to 6 nodes, that means that the computational part is being distributed into 6 different nodes or 4 different nodes. You can see that as we increase the number of nodes, we increase the accuracy of finding that malware, and the training time required for training these distributed convolutional neural network models goes down quite a bit. Now, we did this for actually tumor detection in brains as well. I'll go straight on to the results that if there's a centralized learning platform, it usually had an accuracy of 87%. But if we use federated learning, in which again the data is stored locally and the models are trained locally, but the gradients are shared amongst the different participants or nodes, we had a higher accuracy and a less time per epoch during the training time required for each batch to go back and forth for a model to be trained. So the point I'm trying to make here in this slide and the last slide about the results was that we have an advantage using distributed AI infrastructure. So I think I'm running short of time. So I did another work for smart contract vulnerability as well using AI. This was very centralized, but there are a lot of vulnerabilities that exist in smart contracts like reentrancy, integer overflow, underflow, etc. Now we use the BERT model and the CNN models to basically identify these vulnerabilities, and the results were quite impressive in the sense that we had an accuracy of 92.7% to actually accurately identify a certain vulnerability. Now, in a nutshell, this is the last slide, so I think I've got a minute left. In principle, AI is going in the next 7 years is going to grow anywhere from 1 trillion to 4 trillion, depending on the source you use. Cybersecurity itself is about $500 billion worth of potential in the next 7 years by 2030, and blockchain will have potential of almost more than $3 trillion. So if you combine all these 3 areas, basically it's at the nexus of combining 3 quite important areas into one subset. What I have not done yet is basically use this neural net, this distributed AI ecosystem, which we know is more efficient, requires less training time, and integrate into a blockchain architecture, which would allow basically incentivizing of different of different nodes to basically share data or use their computing power, and allow end users such as businesses and companies to use that technology to secure their systems. because blockchain in itself can have a lot of advantages in terms of automation, in terms of data integrity, etc. So I think I'll probably end here. About what we have done. And in a nutshell, we have been able to see that distributed AI is advantageous as compared to centralized AI systems. The distributed nature can have more integrity if we incorporate blockchain into it. This would allow incentivization as well. And hopefully in future, we are going to continue doing this work and build a blockchain platform around this decentralized AI infrastructure for identification of malicious actors and ensuring that cybersecurity is improved for any business or a company. Thank you very much.
Cool. Thank you, Dr. Khan. It's really great. And you got through quite a bit of material. We have a couple of minutes for questions. So if somebody wants to write a question, you can put it into the chat. I will read it out and also put it on screen. But while we wait for that, I wonder if you could maybe tell me, if you were to have an ideal collaborator, let's say a blockchain or a crypto project that has this token layer that could provide more of a incentive through their tokenomics, like what would you need from them, and what are you looking for? What works best with what you've already developed?
Yeah, so actually, it's the only step required is basically building that setup. What I am certain about is that a distributed AI is performing better than centralized AI systems. Cybersecurity is going to be a huge buzzword in the next few years. It already is. It's going to be a huge market. So essentially, it's just being able to put in a team of more dedicated resource and put them at task to build that infrastructure. I think essentially that's the only thing that remains to be done.
Awesome. Okay, I have a question from one of our other presenters today. Pavel asks, what vulnerabilities have you discovered with AI?
Yeah, so basically what we worked on during smart contract vulnerability, there are almost 29 different vulnerabilities that can be identified, but the majority of them, or a bulk of them, are basically can be classified into 7 distinct vulnerabilities that exist in a certain smart contract. Those are reentrancy problems, there are timestamp problems, there are underflow, integer overflow, underflow problems. So there were about 7 that we could identify. It's not as if we were finding a new vulnerability. It was just that we knew what the vulnerabilities are, and if it exists within a smart contract, we have a very high percentage of accuracy with which we can determine that this particular vulnerability exists, or this particular malware exists in a particular software or particular smart contract.
Cool. Good answer. See if anyone else wants to put a question in the chat. If not, so you mentioned 2 different use cases for the work that you've been doing recently, which was slices of brains and assessing whether you saw like tumor risk, and then smart contract vulnerabilities. Could you maybe make a prediction of like what might you work on next? Is it related or something completely different?
Well, actually, so the application is quite different. One is health related, the other is vulnerability related, but in principle the technology or the intellectual property that is being developed to kind of identify them has a lot of commonalities. And the thing that I'm most interested in is to basically take that work and integrate blockchain into it, so that we can have automation, we can have data integrity, and we can incentivize and tokenize, integrate and incorporate tokenization into it. So yeah.
Yeah, I think that makes a lot of sense. Okay, so I've got about a minute left. So yeah, I will thank you very much for your time. I hope you can stick around for our open Q&A session at the end. If not, yeah, thank you very much for your time. I'll take you down and introduce our next speaker. Thank you, Dr. Khan.